Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is transformers. Our objective is to examine the transformer, an electrical device used to step up or step down AC voltage. We'll examine how the turns ratio between the primary and secondary windings of an ideal transformer affect voltage and current, reflected impedance, and power transfer. This lecture operates under the presumption the viewer has more than a passing familiarity with AC power calculation, as illustrated in the AC Power and AC Power Examples lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. Let it be known up front, this lecture is not about the comic book, the television series, nor the truly awful movie franchise based on the popular Transformer series of toys from the dark ages of culture, the 1980s, but rather one of the most useful electrical devices ever invented, also of the same name. Without overstating their importance, transformers are absolutely essential to modern society and make it possible to not only transmit electrical power over vast distances, but also power a range of industrial devices using standardized distribution voltages. Transformers have had a profound impact on the way our society makes use of electrical power. Any individual knowledgeable about the function and construction of transformers can assure you that there is indeed more than meets the eye. A transformer is a device composed of no moving parts used to step up or step down, or if you want to think of it this way, transform voltage. A transformer does so through the process of electromagnetic induction. We'll examine electromagnetic induction in greater detail in later lectures. However, consider a brief summary of the process. Note all diagrams use the perspective of a conventional current. First, you should understand that electricity, movement, and magnetism are a related phenomenon. As current moves through space, it creates a circular magnetic field around it, where the direction of current influences the magnetic field polarity, and the strength of the magnetic field is proportional to the intensity of the current. In summary, when conventional current travels in one direction, the magnetic field will have a given polarity. If current swaps direction, so will the magnetic field polarity. Additionally, more current means a larger magnetic field, and less current means a smaller magnetic field. Given sinusoidal AC voltage continuously changes magnitude and polarity, it inherently contains a changing magnetic field. The electromagnetic induction process itself demonstrates that a voltage differential will be induced across the terminals of a wire loop placed inside a changing magnetic field, where this induced voltage differential is proportional to the rate of change of the magnetic field and the number of turns in the wire loop. In summary, the slower the magnetic field changes and the less loops in this slowly changing magnetic field, the lower the induced voltage. In contrast, the faster the magnetic field changes and the more loops in this rapidly changing magnetic field, the higher the induced voltage. If our loop of wire formed an electrical circuit that included a load, the induced voltage at the terminals of the loop would allow current to flow. This, at its core, is the basis of electrical power generation. Consider the rotor of a turbine, physically moved by water, wind, or expanding steam, where the rotor can essentially be modeled as a stick with a magnet on it, moving in close proximity to the windings on the stator. If the magnet is turned sufficiently rapidly, a large voltage will be induced across the stationary winding with a large number of turns. This same electromagnetic induction phenomenon also forms the basis of the transformer. However, instead of using a physically moving rotor to create a changing magnetic field, one uses another coil of wire in close proximity. The input of the transformer is sometimes called the line or primary side, and the output, the one containing the electrical load, is sometimes called the load or the secondary side. You'll note the basic schematic symbol of a transformer contains two windings or coils in close proximity to one another, directly hinting at its internal construction. Alternating current flowing in the primary coil would create a changing magnetic field. The secondary winding in close proximity to the primary experiences the same changing magnetic field, and via the process of electromagnetic induction, a voltage differential will be developed across the terminals of the secondary winding. Given induced voltage is proportional to the rate of change of the magnetic field, and importantly the number of loops inside the winding, an easy means of changing or transforming output voltage at the secondary is to simply vary the proportion of coils on the secondary with respect to the number of coils on the primary. If the secondary winding contains more turns with respect to the primary winding, a larger output voltage will be developed, and the transformer can be considered a step-up transformer in that the output voltage at the secondary will be higher than the input voltage at the primary. Similarly, if the secondary winding contains less turns with respect to the primary winding, a smaller voltage will be developed, and the transformer can be considered a step-down transformer, in that the output voltage at the secondary will be lower than the input voltage at the primary. In summary, the ratio of the number of turns between the primary and secondary determines the function of the transformer. Before examining this transformative relationship in greater detail, allow me to comment on the degree of coupling between the primary and secondary windings. While it should be obvious that the current flowing in the primary winding magnetically couples the secondary winding to the primary winding, it's also interesting to note that any current flowing in the secondary winding would also magnetically couple the primary winding to the secondary winding. This means that the source and primary winding can in effect see the load on the secondary side of the transformer, despite there being no direct physical nor electrical connection. In fact, the only connection shared by these two windings is wholly magnetic in nature. Can you now dig this on every level that I do? In addition to all the wondrous properties we are about to discuss, the core function of a transformer, if you want to think of it this way, is to transmit electrical power through free space. Put this in your pipe and smoke it. This transmission of power through free space is, however, not without its limits. It is for this reason that transformers ordinarily use an iron core, symbolized as a double bar between the primary and secondary windings. The iron core is substantially more magnetically permeable than air, up to 5,000 times for pure iron. This means that an iron core transformer is far more effective at concentrating the changing magnetic field linking the two windings. Although construction differences vary from manufacturer to manufacturer in use, a general diagram of an iron core transformer looks something like this. Imagine a ring-like structure of iron around which is wrapped the insulated coils of the primary and secondary windings. Any magnetic field generated by the two windings, rather than wandering off and getting into trouble, is instead confined to the iron core, thereby ensuring the two windings remain firmly magnetically coupled. I'll come back to correct this simplified diagram in a later lecture examining losses in non-ideal transformers. Before moving on, let me remind you that transformers necessitate AC voltage, something that cyclically varies both magnitude and polarity to function, since the changing magnetic field is a property essential to the induction process. DC, in contrast, is characterized by a steady-state value of a fixed polarity, meaning DC does not innately carry a changing magnetic field, meaning it cannot be readily transformed. It's for this reason AC has been adopted as the nearly universal standard for power generation and transmission. Additionally, note that since the voltage generated during the induction process is proportional to the rate of change of the magnetic field, high-frequency sinusoidal voltage can dramatically alter the performance of a transformer. We'll explore transformer ratings and high-frequency effects in later lectures. Moving on. As mentioned, the principal means the transformer uses to step up or step down voltage is to vary the proportion of turns on the primary and secondary windings. This relationship is called the turns ratio, and is customarily expressed as the ratio of the number of turns in the primary winding for the corresponding number of turns in the secondary winding. Given voltage is proportional to the rate of change of the magnetic flux and the number of turns, it can be said that the turns ratio between the primary and secondary is directly proportional to the voltage ratio between primary and secondary. Expressed more succinctly, the number of turns in the primary over the number of turns on the secondary equals the input voltage at the primary over the output voltage at the secondary. NP over NS equals EP over ES. By increasing the number of turns on the secondary with respect to the number of windings in the primary, a larger voltage will be developed across the secondary, and the transformer can be considered a step-up transformer, and that output voltage at the secondary will be higher than the input voltage at the primary. Similarly, by decreasing the number of turns in the secondary with respect to the number of windings in the primary, a smaller voltage will be developed across the secondary, and the transformer can be considered a step-down transformer, and that the output voltage at the secondary will be lower than the input voltage at the primary. Consider the following example. If a transformer primary winding contained 300 turns, and the secondary winding contained only 60 turns, we could say the turns ratio is 300 over 60, or just as easily 5:1. Given the larger number of turns in the primary and the smaller number of turns in the secondary, we can expect this transformer to function as a 5:1 step-down transformer, and that we'd expect our output voltage to be 1/5 of the input voltage. If 120 volts was applied to the primary coil of this 5:1 step-down transformer, a simple algebraic rearrangement of our equation demonstrates that 24 volts would be developed across the secondary winding. As we'd expect, the output voltage is 1/5 of the input voltage for a 5:1 step-down transformer. It makes sense. A practical application for a 5:1 step-down transformer might be supplying 24 volts to power the control electronics for a heating and air conditioning device off of commonly available residential 120 volts 60 Hz AC. By simply adjusting the turns ratio of the transformer, a manufacturer could make this device available for a number of different primary voltage levels. Consider this same device necessitating a secondary output of 24 volts AC, however being operated at an increased primary voltage of 240 volts. Substituting in our given voltage values demonstrates this transformer would necessitate a 10:1 step-down transformer to achieve the same output voltage of 24 volts. Note the turns ratio doesn't mean the transformer literally has 10 turns on the primary and 1 turn on the secondary, but rather that the turns ratio is for every 10 turns in the primary, there'll be 1 turn in the secondary. Sticking with our earlier example in which the secondary possessed 60 turns, the primary for this 10:1 step-down transformer would have 10 times this many turns, or 600 turns. Makes sense. Alright, it's your turn. See if you can determine the turns ratio necessary to power the secondary winding with 24 volts AC, given a primary input of 208 volts. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given 208 volts is roughly 8.7 times higher than 24 volts, one might expect an 8.7:1 step-down transformer to fill the need. In keeping with our earlier example in which the secondary possessed 60 turns, the primary winding for this 8.7:1 step-down transformer would have 8.7 times this many turns, or 520 turns. Again, it makes sense. One might think a manufacturer wishing to supply 24 volts AC to some power electronics using 3 different primary voltage levels might necessitate 3 totally different transformers, each with their own specific turns ratio. One with a 10:1 ratio for 240 volt applications, one with an 8.7:1 turns ratio for 208 volt applications, and yet another one with a 5:1 turns ratio for 120 volt applications. However, a simple modification allows a single transformer to perform these different roles. Consider a multi-tap transformer, it being a transformer with different access points or taps on a single winding. For this particular application, consider a transformer with 600 turns in the primary. However, there exist taps or additional points of connection at 520 turns and another at 300 turns. If the secondary is assumed to have 60 turns, the entire 600 turn primary winding would provide a 10:1 turns ratio for 240 volt primary voltages. The 520 turn tap on the primary provides an 8.7:1 turns ratio for 208 volt applications, and finally, the 300 turn tap on the primary provides a 5:1 turns ratio for 120 volt applications. Thus, this single transformer with multiple taps in the primary is suitable for 240 volts, 208 volts, and 120 volt applications by changing a single point of connection. Granted, there's some extra weight involved with this particular transformer. However, the advantages of manufacturing this system using a single component suitable for export to multiple regions using different primary voltages, might outweigh this disadvantage. Transformers needn't always step down primary voltage. Consider a step-up transformer with a 1 to 50 turns ratio used to step up the 690-volt output produced by a wind turbine generator for delivery to the wind farm collector substation, which collects, hence the name, the output of the numerous turbines in the farm. In this occasion, a simple algebraic rearrangement of the turns ratio equation demonstrates the secondary voltage of this step-up transformer to be 34.5 kilovolts. Our output voltage would be 50 times our input, as we'd expect. Consider yet another application of a step-up transformer, in this case the collector substation, stepping up the incoming 34.5 kilovolts, yet again using a transformer with an output of 138 kilovolts for transmission to a distant city. See if you can determine the turns ratio necessary to power the secondary winding with 138 kilovolts using a primary input of 34.5 kilovolts. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following result. Given 138 kilovolts is 4 times higher than 34.5 kilovolts, one might expect a 1 to 4 step-up transformer to fill the needs. Again, it makes sense. Note the turns ratio is 1 to 4, correctly indicating that it is a step-up transformer and not a 4 to 1, incorrectly implying that this is a step-down transformer. The turns ratio is customarily expressed as the number of turns in the primary over the number of turns in the secondary, and not the other way around. Additionally, they're customarily expressed as ratios. Resist the temptation to simplify this to 0.25. Importantly, the turns ratio, primary to secondary, is directly proportional to voltage, primary to secondary. Before we move on, compare and contrast not only the step-down versus step-up relationship of these past example transformers, but also their larger roles. In the first scenario, we made use of a transformer to simply power the control electronics of some heating or air conditioning device, whereas the next series of examples dealt with transformers designed to transmit a massive amount of primary power from some distributed generation equipment to a city some distance away. In this sense, the first couple of examples might be referred to as control transformers, meaning a control transformer is designed to power low-power control electronics only, and not massive amounts of primary power. The second examples, in contrast, might be referred to as power transformer applications, meaning these transformers are designed to change the characteristics of massive amounts of primary power for transmission purposes. As one might expect, a control transformer would be a relatively lightweight, inexpensive affair, and a power transformer must be sufficiently robust to handle the amount of power being transferred. Don't for a moment equate step-up transformer with the term power transformer, because one needn't look any further than the transformer at the distant city being asked to step down the massive amount of power on the 138 kilovolt transmission line to a level more appropriate for distribution to their industrial and residential customers. The step-down transformer at the city would also be classified as a power transformer, since it's changing the electrical characteristics of massive amounts of power for the purposes of transmission. Other types of transformers exist, including, but not limited to, instrumentation transformers, distribution transformers, polyphase transformers, phase shift transformers, and much, much more. We'll examine these transformer applications in later lectures. For now, you should simply realize there exists a range of application-specific transformers, and not all transformers are directly interchangeable with one another. As you're no doubt aware, you can't get something for nothing. Voltage and current are related properties via Ohm's law. Perhaps you've heard of it. Power, another important electrical property, is the product of voltage and current, and this is perhaps the best perspective to approach this relationship from. If we assume a given transformer to be ideal, meaning it is 100% efficient, we can assume all power input to the transformer is transferred to the output with no losses in the transformation. In summary, power in equals power out. I'll come back to explain losses for non-ideal transformers in a later lecture. For now, let's just go with it. Given the function of a transformer is to step up or step down voltage, a given power is a product of voltage and current. If voltage at the secondary input is higher than the primary input, current drawn from the primary must proportionally increase to achieve the required power transfer. Conversely, if voltage at the secondary output is lower than the primary input voltage, current drawn by the primary needn't be as large to transfer the required amount of power. Given voltage and current are related properties, as are voltage and turns ratio, one could express this more succinctly as the number of turns in the secondary over the number of turns in the primary equals the input current through the primary over the output current through the secondary. Ns over Np equals Ip over Is. This makes perfect sense. Voltage has a directly proportional relationship with turns ratio, whereas current has an inversely proportional relationship with turns ratio. Importantly, the current drawn, either from the primary or secondary, will always be reflective of Ohm's law and the load demanding current. Consider an application in which a 5-to-1 step-down transformer is being used to power, let's say, a desk lamp that necessitates 24 volts AC to operate, where the bulb is modeled as a 50 ohm resistor. As we previously demonstrated, this would necessitate a 120 volt AC source in the primary to provide the input voltage necessary for the 5-to-1 step-down transformer to produce the necessary 24 volt AC output. Through simple Ohm's law manipulation, we'd expect the current in the secondary to be 24 over 50, or roughly 480 milliamps. Apparent power is therefore roughly 11.52 volt amperes, all of which is being directed towards 11.5 watts of real power, and none of it towards a reactive interchange, given the bulb is modeled as a purely resistive load. If this ideal transformer was truly 100% efficient, we can say power in equals power out. Given our power output at the primary is 11.5 volt amperes, we could say our power input at the primary to be also 11.5 volt amperes. We can use this power figure to solve for current in the primary. Given apparent power as the complex conjugate of the voltage times the current, we can substitute our given values and solve for the current. Doing so yields a current of only 96 milliamperes drawn from the source by the primary winding. This makes perfect sense. For this step-down transformer, the primary provides high voltage, low current input, where the input power, the product of voltage and current, is 11.5 volt amperes. In contrast, the secondary provides low voltage, high current output, where the output power again is a product of voltage and current, is also 11.5 volt amperes. Additionally, using our previously demonstrated inverse relationship between turns ratio and current, we can also solve for current directly without having to solve for a power intermediary. As we discussed, the number of turns on the secondary over the number of turns on the primary equals the input current through the primary over the output current through the secondary. Ns over Np equals Ip over Is. Given we know the turns ratio to be 5-to-1 and the current drawn by the 50 ohm load from the 24 volt secondary output to be 480 milliamperes, we can substitute in these given values and solve for primary current. Doing so again yields a current drawn by the primary winding from the source to be 96 milliamperes. In summary, given output voltage is 1/5 of input voltage, output current will be 5 times input current. Put another way, given input voltage is 5 times output voltage, input current will be 1/5 times output current. Either way you look at it, there is a directly proportional relationship between turns ratio and voltage, and an inversely proportional relationship with turns ratio and current. In keeping with this observation, see if you can solve for both the secondary and primary current given the same 5-to-1 step-down transformer powered by 120 volts AC input when the bulb modeled as a 50 ohm resistive load is swapped out for one with only 20 ohms of resistance. This might be a high power setting where the desk lamp is being asked to supply more light. Speaking of power, additionally, see if you can solve for power input to and output by the transformer, assuming 100% efficiency. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Ohm's law shows that the 20 ohm resistive load now draws 1.2 amps from the 24 volt secondary output. Given current has an inversely proportional relationship with turns ratio, we find that the primary winding would now draw 240 milliamperes from the 120 volt source. Given these voltage and current values, the apparent power output by the secondary winding would be 28.8 volt amperes, all of which is being directed towards 28.8 watts of real power and none of it towards a reactive interchange. Similarly, assuming 100% efficiency, the apparent power input to the primary winding would be 28.8 volt amperes, all of which is being directed towards 28.8 watts of real power, and none of it towards a reactive interchange. Before moving on, consider the impedance seen by the source through the transformer for both occasions. First with a 50 ohm resistive load, and again with a 20 ohm resistive load. The 120 volt source doesn't know it's being asked to power a 5-to-1 transformer, which in turn is powering these two loads. All the source knows is in the first scenario, it's supplying 96 milliamperes of current, and the second 240 milliamperes of current. My question to you is this: what is the impedance seen by the source through the transformer for both occasions? This phenomenon is known as reflected impedance and has everything to do with the degree of magnetic coupling between the primary and secondary coils. Yes, current flowing in the primary magnetically couples the secondary to the primary. However, current flowing in the secondary also magnetically couples the primary to the secondary. Despite there being no direct physical nor electrical connection between the source and the load, the source still sees an impedance, and current drawn from it will behave according to Ohm's law. In the first scenario, when the bulb is modeled as a 50 ohm resistance, we demonstrated that the source supplies 96 milliamperes of current. Using Ohm's law, this demonstrates that the source in effect sees 1,250 ohms of impedance. In the second scenario, when the load is modeled as a decreased 20 ohm resistance and is drawing more current from the secondary, we demonstrated that the source also supplies an increased amount of 240 milliamperes of current. Using Ohm's law, demonstrate that the source in effect sees 500 ohms of impedance. Pause to consider how the reflected impedance seen by the source, 1250 for the first scenario and 500 ohms for the second scenario, relates to the actual impedance on the secondary, 50 ohms for the first scenario and 20 ohms for the second scenario. You should note that for both occasions, the reflected impedance seen by the source is 25 times that actually on the secondary. 25 times is in fact our turns ratio of 5/1 squared. In addition to the previously discussed relationships for voltage and current and turns ratio, we can also state that the reflected impedance seen by the source is the turns ratio squared times the load impedance. Note, in ideal transformer scenarios, the reflected impedance changes the magnitude of the impedance seen by the source, not its angle. The source in this application sees solely a resistive element with a phase shift of 0 degrees. Let's try a complete example problem illustrating the wonderful utility of turns ratio. Consider a 1.73:1 step-down control transformer powered by 208 volts, providing current to a purely resistive load of 1.6 kiloohms. I'm asking you to solve for the secondary voltage, the secondary current, and the power output by the secondary winding. Additionally, solve for the primary current, the primary power, and the reflected impedance seen by the source. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given our turns ratio is 1.7321 and voltage is directly proportional to turns ratio, primary over secondary, our given values suggest that the secondary output of the transformer will be roughly 120 volts. When 120 volts is applied to a 1.6 kiloohm resistor, Ohm's law demonstrates the current through the load will be roughly 75 milliamperes. The power equations demonstrate that this load will experience 9 volt amperes of apparent power, all of which is being directed towards 9 watts of real power, and none of it towards a reactive interchange, given this is a purely resistive element. Power input would also be 9 volt amperes, all of it being real power. Using either of these power figures, or the inversely proportional relationship of turns ratio and current, we find that the current in the primary will be roughly 43.4 milliamperes. Finally, either the turns ratio squared times load impedance or Ohm's law demonstrate that the source is seeing a reflected impedance of roughly 4.8 kiloohms at an angle of 0 degrees. Additionally, one could have solved for reflected impedance seen by the primary first, and then use this figure to solve for current in the primary. Regardless of the technique or order applied, you should have come up with the same results. That's the point. There's more than one way of getting the correct results, and alternate methods make a great way of checking your work. Let's try another illustrated example, this time featuring a step-up transformer meant to supply 220 volts to a motor modeled as an impedance of 260 ohms at an angle of 32 degrees using 120 volt input. Given this input and the desired output voltage, see if you can determine the required turns ratio, the current in the secondary output, and the power output by the secondary. Additionally, solve for the primary input current, the primary power input, and the reflected impedance seen by this source. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. To step up 120 volt input to 220 volt output would necessitate a transformer with a turns ratio of approximately 1 to 1.83. When 220 volts is applied to our motor winding modeled as an impedance of roughly 260 ohms at an angle of 32 degrees, Ohm's law suggests that the current through the secondary winding will be roughly 846 milliamperes at an angle of negative 32 degrees. The power equations show that this load will experience 186.2 volt amperes of apparent power, 157.9 watts of which is being directed towards real power, and positive 98.6 bars being directed towards a reactive interchange. Power input would also be 157.9 watts and 98.6 bars. Using either of these power figures, or the inversely proportional relationship of turns ratio and current, we find current drawn by the primary will be roughly 1.6 amps at an angle of negative 32 degrees. As can be expected, current drawn by the low voltage primary would be larger than the current drawn by the high voltage secondary to transfer the required amount of power. Finally, either the turns ratio of 1 over 1.83 squared times load impedance or Ohm's law demonstrates that the source is seeing a reflected impedance of roughly 77.6 ohms at an angle of positive 32 degrees. Alright, I do believe I've covered everything I intended to in this particular lecture. We'll examine transformer efficiency and voltage regulation, as well as transformer winding polarity and different types of transformer connections in later lectures. Before closing out this particular lecture, however, let me answer this very pertinent question. Why transform at all? The simple answer might be because different devices necessitate different voltage levels. Consider a transformer primary supplied by incoming 600 volts. However, it contains not one, but several different secondary windings. One with a 1.25 to 1 turns ratio, another with a 2.5 to 1 turns ratio, and yet another with a 5 to 1 turns ratio. Given turns ratio is directly proportional to voltage, it can be demonstrated that the first secondary winding will have an output voltage of 480 volts, the second secondary winding will have an output voltage of 240 volts, and finally the third secondary winding will have an output voltage of 120 volts. This single transformer with multiple secondary windings, each with a different turns ratio with respect to the primary input coil, thus serves as a centralized means of distributing and isolating 3 different voltage surface levels for 3 different intended purposes. For example, the 480 volt output could serve as some hoist, the 240 volt output could serve as some heater, and finally the 120 volt output could serve as some shop lights, a couple outlets, and maybe power our computer. In a larger sense, transformers are absolutely essential to getting power from where it's generated to where it's being used. Step-up transformers make it possible to transmit massive amounts of power over long distances with extremely small losses. Allow me to demonstrate. For this example, let's assume voltage and current are perfectly in phase with one another, and as such, all of apparent power will be directed towards real power and none of it towards a reactive interchange. Consider a 500 kilowatt generator that operates at 690 volts. A simple algebraic rearrangement of the apparent power formula suggests that this generator is producing approximately 724.6 amps, an astronomical amount of current. Now, consider this generator being asked to supply power to a city 200 plus miles away with a long transmission line made of thick, highly conductive, extremely expensive material is modeled as a 0.5 ohm resistor. You'd think 0.5 ohms of resistance might not be a deal breaker, but recall that power is proportional to current squared times resistance. With such an astronomical amount of current being sent through this line, we might expect there to be a large power loss in the line alone. Given the generator is forcing 724.6 amps through the 0.5 ohm transmission line, the power equation shows that the line alone is dissipating roughly 262.5 kilowatts of the available 500 kilowatts, leaving only 237.5 kilowatts, less than half the original 500 kilowatts, available for use at the distant city. Ohm's law additionally suggests that there will be a 362.3 voltage drop across the line, leaving only 690 minus 362.3, or 327.7 volts at the distant city. This transmission scheme without transformation is essentially wasting more than half the power generated just getting it to the point of use. Rather than serving to transmit power, we've effectively turned the transmission line into a 200-mile-long toaster. This will not work, and another means of transmitting power over long distances must be employed. A far better solution to this conundrum is to use two transformers, one at each end of the long transmission line. The first being the transmission transformer at the point of generation, which steps voltage up from 690 volts to 34.5 kilovolts, and the second being a distribution transformer at the point of use, which steps transmission voltage down to an appropriate level for a delivery to industrial and residential users. We'll concern ourselves largely with the transmission transformer for this illustrated example. Given the 1 to 50 step-up transmission transformer is increasing voltage 50 times, current will be 50 times lower. That's the point of a step-up transformer. By stepping up voltage, we can step down current, yet still transmit the same amount of power. Given the 500 kilowatt generator must supply 724.6 amps to the input of the transformer to deliver the required 500 kilowatts of power at 690 volts. It can be demonstrated the output current of the secondary winding will only be 14.5 amps. Given only 14.5 amps of current is now traveling through the 0.5 ohm transmission line, the power equation shows that the line is now dissipating only roughly 105 watts of the available 500 kilowatts, leaving a substantially larger portion of 499.9 kilowatts, essentially all that was generated, available for use at the distant city. Ohm's law additionally suggests that there will be only a 7.2 volt drop across the line, leaving 34,492.8 volts at the distribution transformer in the distant city. In fact, the power losses and voltage drop across the line are so small in comparison, they're almost negligible. By stepping up voltage and proportionally stepping down current, we transfer a significantly larger portion of the original power generated by the remote facility to the city with less line losses. This, above all the other numerous benefits and applications, is why the transformer is such an integral part of modern society. For a device with no moving parts, I find the utility of the transformer absolutely fascinating. Alright, that's about it for now. In conclusion, this lecture examined the transformer, an electrical device used to step up or step down AC voltage. We learned the turns ratio, the number of turns on the primary, over the number of turns on the secondary, is directly proportional to voltage and inversely proportional to current. Additionally, we learned that a source supplying current to an ideal transformer sees a reflected impedance equal to the load impedance times the turns ratio squared. We assumed ideal transformers are 100% efficient, and operating under this somewhat dubious assumption, we can say power in equals power out. Finally, we learned that transformers are an essential component of the modern electrical grid and make it possible to transmit electrical power over vast distances with minimal losses. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.